In this video, we're going to deal with more continuity at a point, but in a different sense. In the previous three videos for this section, we've been given a function that's fully defined for us, like the definition of the function has been given to us, f of x equals something, and been asked to evaluate a couple points, maybe just one point, and see whether or not the function's continuous at that point. Here, what we're doing instead is we're given this unknown value a in one piece of this piecewise function, and we're asked the question, what value of a makes this function continuous, this piecewise function continuous here? If we look at each piece of the piecewise function first, we see that by nature, this quadratic right here, this x squared, and this linear function, those are continuous on all real numbers by nature as far as their domain goes. So they're continuous from negative infinity to infinity if we were looking at just this or just this. So whatever x values they're defined on, we know that those values are defined. The only real place of interest that we have for this question to make sure that this function is continuous everywhere would be at -2, because anything less than -2 is going to be continuous by nature of this quadratic, and anything greater than -2 is going to be continuous by nature of the linear function. So what we need to ask ourselves is what value of a makes this piecewise function continuous at -2? In order to have that, we know that to be continuous at -2, f of -2 has to equal limit as x approaches -2 of f of x. So we can't really plug in -2 into f of x yet to figure out what that value returns because we're dealing with this unknown value first. So that f of -2 is going to have to wait until we figure out what this a could possibly be, and that will almost be our way to check our answer to make sure we get the right a. So what we're going to need to do first is we're going to need to analyze this limit of f of x as x approaches -2. And we see that we can't really analyze the limit just by itself as x approaches -2. We're going to need to break it down into its one-sided limits because as x approaches -2 from the right, we're going to be dealing with this piece of the piecewise function, and as x approaches -2 from the left, we're going to be dealing with this piece. So in order for this limit to be equal to whatever value we think this could be, this limit has to exist, first and foremost. And for that limit to exist, the left and right-handed limits have to agree on what the limit is. So let's come over here and analyze what the left-sided limit and the right-sided limit of our function is. So the limit as x approaches -2 from the left of f of x is going to be the limit as x approaches -2 from the left of ax squared minus 7. Since this is still dealing with this a, this unknown value that we have, let's skip this part for now and analyze the limit as x approaches -2 from the right. Because if we analyze this part first, the only unknown that we have is our variable, and we know that's approaching -2 from the right, so we can at least figure out what value this function's approaching to see what we need to make our a value to make it approach that same value as x approaches -2 from the left. Okay, so let's look at analyzing this piece first. As x approaches -2 from the right, we're first going to look at this product here. So as this happens, 3x will approach -6 from the right. Because as we get arbitrarily closer and closer to -2 from the right, we're going to be getting closer and closer to the multiplication of 3 times -2, which is -6. So we're going to keep approaching -6. We're going to approach -6 from the right direction. And then we look at this sum here. As we get closer and closer to -6, the sum, 3x plus 5, will approach -1 from the right. Because after a certain point, this product here will be greater than, or will be less than -5 in a sense, right? So as it gets closer to -6, this sum here will end up moving closer and closer to -1. So we see that this sum alone approaches -1, but since we have this negative being multiplied to this part of the function, we know that negative 3x plus 5 will now approach 1 instead of -1, and it'll approach 1 from the left, more specifically. So the limit as x approaches -2 from the right, we get 1. So the right-sided limit is 1. So what we need to do is we need to figure out what value of a makes the limit as x approaches negative 2 from the left equal to 1. So let's go ahead and write that down mathematically. Need a such that, so make a little note to ourselves, limit as x approaches negative 2 from the left, ax squared minus 7. So what we're going to do from here is we're going to pass to the limit for x approaches negative 2 from the left, and we're going to solve for a. Okay, so let's go ahead and do that. So we get a times negative 2 squared minus 7. Or we get 1 equals 4a minus 7. 8 equals 4a. Divide by 4. A equals 2. So we have maybe a value of a equals 2. What happens when a equals 2 is the right-sided limit doesn't depend on it, but it returns 1. And in order for the left-sided limit and the right-sided limit to agree, we know they both have to be equal to 1, and the number that makes that happen is 2. So if we plug in 2 for a, we see that our left-sided limit also is equivalent to 1. Okay? So when our left-sided limit and our right-sided limit agree, we know that the limit, in more of a broad sense, as x approaches negative 2 of f of x, exists, and it's that thing that they both agree on. So we have this. In order for our function to be continuous at negative 2, we need the limit of f of x as x approaches negative 2, which is 1, to be equal to f of negative 2. What happens when we plug in negative 2 here? Well, in order for that to happen, let's check and see what happens when we plug in our a value that we found in, as well as plugging in negative 2 for x. So when we evaluate f of negative 2, we're going to be concerned with this piece. Okay, and we said, okay, a is 2. So let's go ahead and check that first. Make sure we plug that in. 2x squared minus 7. And so now, let's plug in negative 2 for x. So we get f of negative 2 is 2 times negative 2 squared minus 7, or 2 times 4 minus 7, or 8 minus 7, which is 1. So f of negative 2 is 1. The limit as x approaches negative 2 of f of x is 1 when a equals 2. So now we have found the value that makes f of x continuous from negative infinity to positive infinity.